Okay. So the starting point is A is not positive definite. Okay. So Hessian modification simply says that I need to perturb the matrix to A plus delta A such that it becomes positive definite. Now this sounds like a very loose thing, right? Perturb it. Of course I can perturb it to anything I want and it will become a positive definite matrix, right? So there is a little bit of care that I have to take. So you would want to perturb it in such a way that it has as low norm as possible. You can say that. You can make by the meaning of a perturbation is it's small compared to the original. So you can say or rather require that the norm of delta A be as if the norm is as low as possible, what is the advantage? I have changed my problem as less as possible. Because I can change my A to whatever I want. I can just take all the eigenvalues and replace them by +1 everywhere and solve that and feel very good about myself. But I've changed the original problem. When I go back to my original problem, I'll see that the solution doesn't match. So I don't want to modify the problem too much. The way for me to ensure it is to say that whatever you do, whatever perturbation you do, make sure it has a low norm. Okay. Now can we try to guess how we should perturb this? Do you want to think about it for a second? Kill the largest, so let's talk independent of the method of evaluating positive definite. So Gershko and Disturum gave us the disks, okay? But assume that you have enough computing power that any of these three methods, A, B and C are available for you, okay? So how would we work it out? How would we work out this minimum norm? What can we start with? So A, let me give you a hint. So A is, let us say, Q lambda Q transpose. Okay. Some of these eigenvalues are negative, which is why it's not positive definite. Now I am adding delta A. Okay. Is there a way you can think of by which this can happen so that I can use this eigenvalue decomposition of A? Okay, that's a good idea. So what she is suggesting is that the eigenvalues of delta A should be in such a way that they bring the negative eigenvalues of A into the positive range. Okay. Now, is it possible for you to, okay, let me put it another way. For which matrix can you just look at it and tell the eigenvalues? Diagonal matrix. What is the easiest diagonal matrix you can think of? Identity. But if I do identity, what are the eigenvalues? 1. Do we want 1? What do we want? We don't know what we want. It depends on A. How about if I do this? What are the eigenvalues of this guy? Tau. Earlier it was 1, now it's tau. Now this tau is just a scalar, remember? Can I write identity in a clever way? QQ transpose. Very good. So what is A plus delta A? Can I group the Q's and the Q transposes in a nice way? Right. So I'm going to get Q lambda plus what? Tau I Q transpose. Quite easy. So do I get a value of tau that is required now? Right. So the eigenvalues that are going to come from here, so I'm going to get lambda min plus tau. This is going to be the lowest eigenvalue of this new system. And what should this be? Greater than 0. Right. So should I put it greater than 0? So greater than 0 can be tricky because why? Supposing it's 10 to the minus 15, is it greater than 0? It is greater. Is it a good idea? Why? Condition number will become insane, right? So at this point itself, may as well make your life a little bit simpler. Instead of saying 0, what should you do? Put some threshold, and this threshold you keep in your hand. You can control it. Okay? So this saves you from a bad condition number. Okay? So that tells you that this value of tau is greater than equal to delta minus. And all of this exercise is of meaning only if lambda min is actually less than 0. If it's already positive, there is no point. Right? So this is what is meant by, so okay, and to complete the thing, what is norm of delta A? If I were to take your favorite norm, what would be this? What is the norm of identity matrix? 1. If, for example, take the Frobenius norm, it's 1. So this is actually just going to be tau. Okay? Norm of delta A. So now by making delta as small as possible, I can say that this is the minimum norm perturbation to the matrix A such that my new Hessian is positive definite. It's not a new Hessian, it's a Hessian modification. It is not the Hessian of any problem. I've just modified it. So with this Hessian modification in place, yeah. Correct, yeah, it has a condition number 1. Condition number 1, correct. That's good. What does that got to do with norm? Condition number and norm are different. If you're thinking of the definition, what is the norm of delta A inverse? 1 by tau. So condition number is 1. What qualifies as a good approximation? So this is not an approximation of the Hessian. This is a Hessian modification. We are modifying it with the least norm way to arrive at a matrix which is positive definite, and then we continue the rest of the procedure. Correct. So if you look at the very first step over here that we have, where we summarize the Newton method, right? If Bk is not positive definite in step 2, you are suggesting that I chuck Bk and I pick any other matrix. Yeah, why is that a good idea? Okay, so that's a good question. So how did we come upon this expression of minus Bk inverse grad Fk? Does anyone remember? We took the second order Taylor expansion of f and then we minimized it and we came upon exactly this expression. So if I choose exactly this expression, I am coming to a minima of a quadratic expression. If I replace this Bk by any other matrix, that's no longer a minima. Right? So that's why I want to be as close to the original Hessian as possible so that I get the property of that second order convergence and approximation of Taylor. If I replace this, it will be a legitimate descent direction, I agree, but it may not be the best descent direction. Okay? But that said, like I said at the start of the class, there are a full family of methods which talk about what is the best way to perturb this Hessian so that I am as close to the quadratic approximation and I am getting good properties of convergence. So this is just one of many, and this is the simplest way. There are much more sophisticated ways also. So just a descent direction is not good enough because you saw in the case of steepest descent versus CG, just a descent direction got you a certain rate of convergence. When we move to CG, you got much faster convergence, right? So just a descent direction, it works, but you can do better. That's the motivation. Yeah. Root 3 into tau. Why root? Oh, you will get a root n. Correct. With the Frobenius norm, you would get root n. With the 2 norm, what would you get? 1 only. Right. So, okay. So, this, let's just make it. Okay. Yeah, question. How do you know lambda min? You come to these 3 methods. So, you would. It does, right? Because, in fact, I would do the disk theorem in this case because it is saying that your tau should be delta minus lambda min. So, your question is, how do I know lambda min, right? To find out lambda min, what should I do? I look at the circle which is to the left, which is coming closest to the origin. So, let us say, for example, let's take a good example, right? So, all my disks were like this. In this case, my lambda min, for example, will be somewhere in this disk. It's positive definite. Now, what happened? Let us say one disk became like this, and I have this over here. So, I have not actually computed lambda min. I am saying lambda min lives in this disk. Now, what do I need to do? It may be positive. Yeah. So, this is because I am putting less effort, I am also getting a rough answer. I am saying that it lives in this disk. Where in this disk, I don't know. So, you are right. The eigenvalue could be here. Lambda min could be this, right? So, I am losing this information because I am virtually putting in no effort. But this disk, if I move by this amount to the right, then I am assured that lambda min is greater than 0. So, I am trading off accuracy for computation power. Okay. That is why this method is, particularly if you are looking at a big data problem, this becomes very attractive. Right? It's simple enough to just modify. And so this, one may ask that, I'm perturbing the Hessian, how is it going to work out? Because I'm actually changing the problem. Now, what happens is that if, again, I'm going to state this without proof, if your function is a well-behaved function in the sense that it is twice continuously differentiable, Lipschitz continuous, all of that, then as you approach the solution point, the Hessian becomes positive definite. So, as you approach the solution, it turns out that the Hessian becomes positive definite, and this is proven in the book. So, as I approach the true solution, I actually don't need to do Hessian modifications. I use the straightforward Newton method, which gets me. So, that we just get that for free. Yeah, that's what we push the disk. Whichever disk has the leftmost point, I move that to the right. No, I'm only pushing one disk to the right. Oh, okay, I'm correct. I'm pushing all of the disks to the right. So what? Okay, right. So what he's saying is, why push all of the disks by amount tau to the right? Why not just push the offending disk to the right? Okay. So what would that, or what kind of a delta A would that correspond to? Tau, right? That is also possible. So what he's saying is that instead of pushing everything by tau times identity, have a diagonal matrix where there are the non-zero entries are only for the disks which are overflowing onto the left. Push them to the right? And then when you look at A plus delta A, you would have all the disks are now on the right. Some of the disks are not modified, and some disks are modified. That's what you're suggesting. Yeah. So there is a full family and range of solutions possible over here. And they're all like, give varying amounts of accuracy. And that's a good idea. In that case, what would be the norm of delta A? Frobenius norm would be lesser, and probably the 2 norm may also be lesser. We can compute that. Okay, so I think with that I'll bring this to an end, because the next thing, I don't want to start quasi-Newton method and then have to stop in 5 minutes. Okay, so we're in the next class we'll look at quasi-Newton methods. The advantage of a quasi-Newton method, so quasi-Newton methods sit between Newton methods and steepest descent methods. Quasi-Newton methods give you superlinear convergence, rate of convergence. So it's not as good as quadratic, but it's better than linear rate of convergence. So we'll look at that tomorrow in detail. Right. A is the Hessian, yeah.
What happens if we modify and then after modification the condition number of the Hessian became very high?
That is in your hand. So if the modification is in your hand because of this value of delta over here. If you chose, because you are modifying the smallest eigenvalue, if delta ended up being very small, then your condition number is very high. So don't make delta small. Make it larger so that the eigenvalue, the lowest eigenvalue of A plus delta A is not very, very low. That you can do by choosing delta. Again, there's a trade-off. The more you modify it, the further you are going away from the original problem. So you have to have this trade-off in mind. Yeah, but keep in mind the nuances of this Gershgoren disk theorem. It can sometimes give you some misleading interpretation if you don't look at it carefully. It is only saying the eigenvalue is somewhere in the disk. It's giving you no information of where it is in the disk. So even though part of the disk may be in the left half, it is no guarantee that the eigenvalue will be there. It can be anywhere in there. So you may be doing more work for no reason, but you can't know it unless you spend order n cube effort. If your Hessian is positive definite, then you will simply use this Newton direction. You will not do any modification. Correct. Correct. Yeah, you have to each time determine whether or not it is positive definite. Not using the disk method, using whichever method. Disk method is one example of 3 methods. Right? Now, if you have an inaccurate method, then you are likely to go off course. So again there you can have a mix. Sometimes you could do this method, sometimes you could do that method, depending on how much accuracy you want. You could do that also. The difficulty there is that if you end up, if it is not a descent direction and you didn't check for it, then actually you ended up going in the ascent direction. So you made your problem worse. So whether or not it is a descent direction should be checked at each iteration. Right? In fact, if you don't check whether it's a descent direction, your step 3 will actually never converge. In the backtracking line search, when you're either doing sufficient decrease or curvature condition, all of that assumes that the PK is a descent direction, but actually your PK is a ascent direction and you didn't check it. So your step 3 itself will give you a problem. So you have to check this every time. How you check it? You could vary the accuracy at each step, but you must check it each time. Yeah, question? Yes, so okay, two responses. When I'm changing it, when I'm changing the Hessian, I'm trying to make sure that the norm of the change is as low as possible. Okay. So I'm changing the original problem. Right? Now, as what I mentioned a few minutes ago, as I actually approach my true solution, the true stationary point, if the function f has all of these nice properties, it turns out that the Hessian is positive definite. So you will end up not requiring the modification. And so that's why you end up in the correct solution. Okay. If that were not the case, we would be in real trouble. Then we would have solved a different problem altogether. So this is somewhere from between your starting point and your solution, somewhere in the middle you have to do all of these tricks. Okay, if you have no more questions, you can give us your feedback chits. See you tomorrow. The rate will still be quadratic, but because it's positive definite. Yeah, the modified Hessian is still positive definite, but it's not completely, yeah. So maybe you could say that the rate of the coefficient of the rate of convergence now change. But the rate will still be quadratic. I mean, you may be going at a quadratic rate to a wrong answer in between. Towards the end, you will get back to it.